So my name's Alex Hodnett. I'm with Chem Aqua. I'm territory manager and area technical lead as well. Been with Chem Aqua for 7 years. We specialize in commercial and industrial water treatment. Appreciate all y'all coming today. Does anybody have anything specific that they want to try to touch on, or is this kind of just new for everybody? Pretty new for everybody? Okay. So what we're going to talk about mostly is why do we treat water? So we're going to talk about that. We're going to talk about the impact of water treatment on operating costs, the importance of pre-treatment application, control equipment. We're not really going to get into too much of how water treatment can help you be more green today. But let's start with why do we treat cooling systems primarily. So maximizes system life, efficiency, reliability, and also public safety. It's going to minimize operating costs, minimize fuel, water usage, minimize chemicals, minimize maintenance, and minimize labor. So some of the problems that we're trying to protect against, and again, we're not going to get too much into boilers today, but in cooling systems, we're trying to prevent corrosion, deposits, microbial growth, scale, anything that is going to form insulating films or scale or anything like that on heat transfer surfaces. So primarily in cooling systems, whether it's cooling towers, chillers, anything like that, we want to make sure that you have good heat transfer so that we're able to remove that heat from your refrigerant effectively, efficiently. That's going to help your compressor not have to work as hard. You're going to get a better temperature split across your cooling tower, so we're going to get into all that kind of stuff today. So the first thing, water itself. So obviously, water's colorless, odorless, tasteless. Chemically, we call it H2O. Water is one of the cheapest, best things that you can use for heat transfer. So that's one of the reasons that it's readily available. That's why we use it. It's also called the universal solvent. So, as you know, like Grand Canyon, right? Like over time, if water flows through something enough, it's just going to erode it away. It has the ability to dissolve pretty much almost anything if given enough time. There's also impurities in water that cause corrosion, deposits, and all the problems that we're talking about. The water picks up all of that through the hydrologic cycle, which we're going to talk about that as well. So basically, as water evaporates from streams, rivers, oceans, whatever it is, as it goes through the hydrologic cycle, it picks up dissolved gases, dissolved solids, suspended solids. All these things can end up causing problems when it comes to industrial water treatment. And everywhere has different water quality for a variety of different reasons. So, as far as dissolved solids go, what's the primary dissolved solid that we deal with here in New Orleans that causes problems? Anybody know? Calcium, yeah. So calcium and magnesium contribute to the hardness that we have in New Orleans. We have anywhere between about, depending on the time of year, 160 ppm to sometimes up to about 220 ppm of total hardness. Total hardness is going to be your calcium hardness plus your magnesium hardness. When those two combine, so like the scale that you see on cooling towers and stuff like that, that's calcium carbonate scale. That's a combination of calcium and magnesium. You have to have the magnesium present for it to form calcium carbonate scale. So we're dealing with that. We're dealing with pH. We're dealing with alkalinity. We have high alkalinity here in New Orleans. We have relatively high pH as well. That primarily comes from the amount of hardness that we have. And then also one of the issues that we're going to have in cooling systems is dissolved oxygen. Dissolved oxygen can cause pitting corrosion issues, so that's something that we have to keep in mind as well. All right, what is that? Does anybody know? It's old school. They're a lot different now. They're digital, but yeah, it's a conductivity meter. So conductivity is actually the electrical conductivity of water, but we use it to determine basically the dissolved solids in the water. The old way to do it was total dissolved solids, TDS. Now we use conductivity as the way that we measure the total dissolved solids in the water. The higher the conductivity, the more dissolved solids. The lower the conductivity, the less dissolved solids.
Does sodium have a factor in that?
Sodium, yes. Yeah. So.
Sodium is going to throw off the target?
Yeah. So if you were to take like a glass of water and dissolve salt in it, measure the conductivity, and then dissolve more salt in it, the conductivity is going to go up. So it's all dissolved solids are going to have an impact on conductivity, but there's only certain dissolved solids that are going to be limiting factors in terms of your water treatment. So sodium, for the most part, is not an issue. Sodium chloride is an issue because that's salt, right? But sodium itself is not a problem. All right, so we have the pH scale here. Furthest towards 1, furthest away from 7. Going that way is going to be acidic. This way is alkaline. In New Orleans, we have about 9 pH, which, you know, is a little bit on the higher side, but it's not an uncomfortable pH. One of the things that we do have to deal with here with that pH is the higher the pH, the less effective oxidizing biocides can be. So that's one thing that we have to take in consideration if we're feeding sodium hypochlorite, which is bleach, or bromine. We have to make sure that we're feeding enough of that product for biological control, given the higher pH. Lower pH is easier for it to be effective. Did you have a question? You looked like you were.
Y'all, you use bromine to treat water?
Yeah.
Okay.
Yeah.
That's interesting.
Yeah, not drinking water. None of this is about drinking water.
Obviously, right? But
yeah,
that's interesting.
Yeah, it breaks down into chlorine. So it's kind of a combination product, like a hypobromo chloro type of, you also have hypobromous acid, which can be used as well. We don't do any kind of pool treatment, but if you know people that do like swimming pool treatment, you'll notice that sometimes people will want to bring the pH of the water down. A lot of that is because the chlorine is more effective at a lower pH. So if like you're at 7.5, your chlorine is going to be more effective than at 9.
But then the lower the pH, the greater the potential for corrosion?
Correct. Yeah. So you don't want to like depress the pH to where it's acidic, and we don't do any kind of pH depression with our water treatment here in New Orleans for cooling towers. Like, we can feed enough chlorine, whether it's bromine or whether it's bleach, we can feed enough for it to be effective without having to depress the pH. All right, so we talked about hardness. That's a pretty cool picture right there of kind of what can happen over time. So I'm not exactly sure in that picture what type of pipe or tube that is, but if you ever see anything remotely similar to that in your condenser tubes, you have like a really, really big problem. So there's a distinction that I want to talk about because it's a big misconception and there's a lot of confusion in water treatment about it. So I'm sure y'all have seen cooling tower fill where you see calcium buildup on the fill. If that calcium buildup on the fill is in an area where there's constant water flow, that's a water treatment issue. If that buildup on the fill is in an area where there's intermittent water flow, that's evaporative deposits. So when a cooling tower operates, your fan speed is variable depending on your load, right? And so if the fan speed is full out, that water curtain that's going through the fill is going to be pulled inwards. As your load drops off, that water curtain goes back out because the fan is not inducing airflow at as high of a rate. So the outer edges of your fill end up having intermittent wet and dry conditions, and because of that, you're going to have evaporative deposits that build up on the outer edges of the fill. If you look in a cooling tower on the back side of your fill where there's constant water flow, if you have a bunch of scale buildup on that side, you have a water treatment issue. The reason I say that is, let's pretend these are condenser tubes on your chiller. If you see that kind of scaling in a condenser tube, that's something that's a constantly wet surface. That means that calcium is precipitating. It's coming out of solution. It's no longer dissolved. And so that means that typically your cycles of concentration are too high. We're going to get into cycles and all of that as well today. But that's how that can happen. And that,
you could even run a chiller with that much.
Probably not. That's probably some other kind of
Will shut off.
on high head pressure.
Yeah. Once your approach gets to 5, then.
Yeah. Yeah, I mean, your compressor has to work so hard at that point.
Yeah, there's no check.
Yeah, I mean, I've never seen a condenser tube that bad. I've seen some bad ones, but that's probably some other kind of piping, honestly. Yeah, you will see PVC like that sometimes, especially downstream from where the chemical is injected, if it's like a chemical injection loop. So what can happen is when you inject, especially chlorine and bromine, into condenser water, high pH condenser water, downstream from that chemical injection, you can have localized scaling just because of the interaction of the chlorine with the high pH, high alkalinity water. It will cause localized calcium precipitation in that line. So that's like a good preventative maintenance thing for engineers just to be aware of, because it can cause flow issues through your chemical control loop for sure. So we talked about oxygen a little bit earlier. So oxygen, especially in a cooling tower system, condenser water is loaded with dissolved oxygen, just by virtue of the fact of how a cooling tower operates. You got a fan that is pulling a bunch of air through that fill. There's a lot of intimate contact between that air and the water, which is how you remove the heat from the water. That's how you create that accelerated evaporation. But in doing so, you also end up putting a lot of dissolved oxygen in that water. And so that can cause corrosion issues. That's part of the reason that the inhibitor that we use is a combination scale and corrosion inhibitor. All right, so we got a few things here. So you got some pretty bad corrosion issues over there on those condenser tubes. It's kind of hard to see, but we have a little bit of scaling and biofouling on these tubes as well as the tube sheet. All right. So here we have a diagram of kind of how all this operates. For any kind of plant, a lot of your energy cost is going to be directly related to your compressor. Like that's what all of your electrical costs. So having clean heat transfer surfaces is absolutely huge. Having clean cooling tower fill is huge. The Cooling Tower Institute recommends at a minimum once a year tower cleaning. A lot of people don't want to spend money on doing the cooling tower, but that extra 1 or 2 degrees of temperature split that you get can make all the difference in the world. It's probably over a period of a year going to pay for the cooling tower cleaning and the energy savings that you're going to get. All right. So here we have a pretty cool picture of corrosion. So that's kind of how corrosion happens. It's not only just metal loss, but it's also deposits. And then if you notice, you can end up having a corrosive deposit situation, and then right here you have metal loss under that deposit. So that's actually what's called under deposit corrosion. What can happen a lot of times when corrosion starts building up, you can have bacteria colonies that are living underneath those deposits, and they start corroding out the metal underneath. And so that's a big cause of catastrophic failure due to corrosion. So again, proper inhibitor levels are going to protect against corrosion, but also microbial control is huge in protecting against corrosion. You don't want to bomb a cooling tower with bleach, because then that becomes corrosive. So it's got to be the right amount. But we want to make sure we keep bacteria under control, inhibitor levels correct. It's all kind of a delicate balance. So here you got some mineral scaling in those tubes that can cause insulation that's going to inhibit heat transfer. There's also quite a bit of slime on those tubes as well. It's funny, there's a lot of people when they do their chiller inspections, they'll go, man, tubes look good. I put my finger in there and they were slick. They were slick. If they're slick, it means you have a biofilm. If it's smooth metal, that's good. If it's slick and slimy, you have a problem. And a lot of people overlook it because they're like, oh, well, I didn't have any scale. Biofilms are actually 4 times more insulating than scale. So if you feel like a really slick, slimy tube, you probably have more of a water treatment issue than you would if you had a little bit of scale in there. All right. Does anybody know, I'm sure everybody's heard the term, but cycles of concentration. Does anybody have a handle on what that is and why it's important? Not really. Okay. So, it's good. It's one of the biggest parts of water treatment. It's one of the most important things. So, a lot of people think that water treatment is just chemicals. If you don't have proper blowdown where you can control your cycles of concentration correctly, you don't have water treatment. It does not matter how much chemical you feed. Proper blowdown control is the most important, most critical thing about water treatment. In New Orleans, we base conductivity set points based on how much dissolved solids we know that we can keep dissolved. So the chemical that we're feeding has polymers in it that allow us to keep mineral content to a certain point. It's called the saturation index. So if you think about like a glass of sweet tea, you put sugar in the sweet tea and you stir it, it's going to dissolve. If you put some more and you stir it, it's going to dissolve, maybe. Up to a certain point, and then you're going to see that sugar start settling out in the bottom of the glass. So every liquid has a saturation point of what can remain dissolved in it, and before it's going to precipitate out into, in this case, scale. So I'm going to draw a little diagram for you guys so we can talk about cycles. We're going to pretend that this is a cooling tower. This is going to be your makeup. This is evaporation. And this is going to be your blowdown, and this is your water level here in the cooling tower. So let's pretend this is the first time that this cooling tower has been put in service, okay? And let's say that we fill it up with 1,000 gallons of water. And we're not going to talk about conductivity. We're going to pretend that the dissolved solids right now are marbles, okay? But it's dissolved. It's not suspended, but we're just going to illustrate it by pretending that it's marbles. So let's say we filled it up with 1,000 gallons of water, and in that 1,000 gallons of water, let's say there are 10 marbles. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right. If we evaporate half of the water in that cooling tower during that cooling tower's operation, we evaporated 500 gallons of water, right? How many marbles are there after we evaporated 500 gallons of water? 10. That's right. There's still 10 marbles. The dissolved solids that are in the water cannot leave with the evaporation. The only thing that leaves is the water. But you've got to make up that water loss that you just evaporated. So if you evaporated 500 gallons, you've got to bring in another 500 gallons, right? Well, you're bringing in 5 more marbles. Does that make sense? 1, 2, 3, 4, 5. Huh? Right. So now we have 15 marbles dissolved in the water. If we evaporate another 500 gallons, we got to make up that water loss. So by bringing in that much more water, we just brought in another 5 marbles. At some point, depending on the water chemistry, the type of chemical that you're feeding and everything like that, you're no longer going to be able to keep all those marbles dissolved, and they're going to start precipitating out as scale on your tubes. That's how we choose a conductivity set point, and this is what cycles is, all right? So when we first filled it up with 1,000 gallons and we had 10 marbles, we were at 1 cycle. When we evaporated 500 gallons and we added another 5, we're at 1.5 cycles. When we evaporated another 500 gallons and added another 5, we're at 2 cycles, okay? Does that make sense? Because 10 marbles just became 20. 2 cycles. 10 times 2, 20. Do it again, 500, 5 more marbles, do it again, 500 gallons evaporated, 5 more marbles. 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. Now we've got 30 marbles with 3 cycles. So let's pretend that 3 cycles is what we want our set point to be. If our incoming conductivity was 500, and we're at 3 cycles of concentration, our conductivity is now 1,500 conductivity. Does that make sense? Kind of, sort of? Now, if we're talking about this instead of marbles, if we're talking about this as ppm of hardness, if we started with 200 ppm of hardness, at 3 cycles, we got 600 ppm of hardness. So your city water conductivity was 500, 3 cycles, your set point's now 1,500. You had 200 total hardness in your city water, 3 cycles, now you have 600 ppm. So the marbles is kind of a rudimentary way to illustrate ppm of hardness. You can only cycle that up to a certain point before it becomes oversaturated, and it's going to precipitate out and start causing problems. And so that's why blowdown set point, conductivity set points, and cycles are the heart of water treatment. That's why that's so important. If you don't have, and also, just so y'all understand, if this is our set point and we get to this point, that's when the water treatment controller is going to initiate blowdown. We're going to blow down some of that concentrated water that's got 30 marbles dissolved in it, right? And we're going to bring in makeup water that's only got 10. Does that make sense? So we're blowing down something that's more concentrated and bringing in something less concentrated so that we maintain that level of mineral saturation in the water.
Percentage.
Tom?
How do you come up with a percentage to know how much you're blowing down?
Well, your controller has a probe. So it's got a conductivity probe. So if we're trying to maintain a 1,500 set point, it's reading the conductivity of the water. When it gets above 1,500, it's going to kick on that relay for the solenoid to open so that you start blowing down. It's still reading the water coming across that probe. And so once it gets to 1450, we usually put like a 50 deadband on it. Once it gets to 1450, it's going to call for that relay to not be energized, and that solenoid's going to shut and blowdown's going to stop. So that's how we maintain that set point.
So it's summer, common to have it blowing down constant?
It can be. So you have a higher heat load, and so your evaporation rate's a lot higher in the summer. You don't have free cooling. You're having to cool the water by, your fan speed is probably running all out during the summer, right? And so because you have that accelerated evaporation rate, your mineral content in the water is concentrating at a higher rate. And so it can create a situation where you feel like it's almost constantly blowing down. It shouldn't be constantly blowing down. You should have periods where it stops. If it's not stopping, it could be that your blowdown line is restricted so that you're not blowing down at a fast enough rate. You're not discharging enough water fast enough. Do you find that your conductivity is staying at set point, or is it continuing to climb even though it's blowing down?
No, it's dropping.
It's dropping? Okay. So does it go below set point?
Only in the winter, it seems.
Okay. But during the
And
summer?
I noticed that it's not blowing down. I have to start really looking at the map because we do read the meter.
Yeah. During the winter, you're not going to have nearly as much blowdown during the winter. You're going to have.
Seems like so much makeup water.
Yeah. So makeup, it's your, whatever you're losing to evaporation and blowing down, that added together is your makeup. So.
So it doesn't matter if you add more treatment, it won't reduce the makeup water.
Is your question, does more treatment equal the ability to run higher cycles and not have to blow down as much? To a certain point. So again, the saturation point is the saturation point, and that's all based on what the chemical is rated for. The correct answer to your question is it's called the glandular saturation index, and it's on a scale of -3 to +3, and that's all dependent on temperature, the amount of calcium and magnesium hardness in the city water, alkalinity, pH.
At the very end of the line,
In New Orleans,
sitting in Kenner.
yeah. So the city water's pretty standard across the board. Right now it's around 520 conductivity, total hardness is around 190, pH is about 9, alkalinity is about 100, 110. It's pretty standard across the board. So your location within the city isn't going to have too much of an impact.
We said that. I wondered if there's...
Yeah, one thing that is impacted by your location in the city is the city water chlorine levels. So the city has like different injection points in different areas. So you have some areas that have like very little total chlorine in the city water. You have other areas that have really, really high levels because they happen to be like really close to an injection point. So we've had customers before that they've actually had issues with some of their domestic water lines with corrosion because of the city water chlorine levels. So they've had to put in like activated carbon filters to remove the chlorine. So anyway, but the way you decide on a set point is based on the LSI of the water, the glandular saturation index. And that's getting a little bit into the weeds, probably like a little bit more than what we wanted to get into today, but it's a really good question. But essentially, if you take our inhibitor, the 31155 product, it can handle up to 2.5 LSI. The LSI scale is -3 to +3. -3 is corrosive water. 0 is neutral. +3 is very, very scale-forming water. And so basically at about 4 cycles of concentration, we're at about a 2.5 LSI. And so that's as much as our inhibitor can handle, and that's pretty much across the board for all companies. So, if your water treatment company is running somewhere between 3 to 4 cycles, as long as they're feeding the right amount of inhibitor, you should get good results. If you start trying to get into like 5 cycles, 6 cycles, it's going to take that comfy 2.5 LSI number and it's going to drive it over that, closer to 3. And you're going to be in a situation where the inhibitor is not able to handle that amount of dissolved hardness, and it's going to precipitate and start forming scale. So, good question. So another question is, why do we cycle the water up? A lot of people are like, well, wait, if you cycle the water, you have more mineral content, and that increases your chance for scaling. Why would you do that? Why would you just not run lower cycles and you wouldn't have as much of a risk of scaling? So this is an example right here based on a 1,000-ton load, 24 hours a day, 365 days a year. Water costs $3 per 1,000 gallons. Inhibitor costs $2.50 a pound. Inhibitor feed rate 100 ppm. If we only run 2 cycles of concentration, that's your bleed, that's your annual makeup. Going from 2 to 3 cycles, you have that. 3 to 5 cycles, you have that. So you can see that just from going 2 to 3 cycles, you're saving 8 million gallons of makeup a year, which is pretty incredible. So because we're able to feed chemical and keep that hardness dissolved, and we're able to cycle up that water, we're able to save customers tremendous amounts of water versus running lower cycles and just wasting a bunch of water. There's a lot of times that, this is something that, I think everyone should just be aware of. A lot of customers like to do contracts. That's a good thing for you. If you buy chemical as needed, you run the risk with some vendors that they're going to run lower cycles waste more of your water so that you have to buy more chemical. Because the more you're blowing down, the more chemical you have to feed to make up for what you lost in blowdown. So you want to make sure that whoever your water treatment vendor is running the correct amount of cycles. And in New Orleans, that's generally between 3 and 4 cycles. That's going to optimize your water usage, and it's going to minimize your chemical usage. So. We kind of talked about this a little bit earlier. That's a really nice big slug of bioslime there. That can cause a lot of issues like we talked about, fouled heat exchanger surfaces, which causes poor heat transfer, corrosion and metal failure, especially if you have biofilms that are forming underneath deposits that are eating away at metal underneath. We've all heard of Legionella and Legionnaire's disease. That's something we're not going to really get into too much today, but obviously that is a concern, especially at healthcare facilities. We can touch on it just real quick, but it is a multifaceted approach to take care of Legionella. It's not just chemical treatment. It requires preventative maintenance, proper cleanings, proper system maintenance, all of that. So that's another reason that cooling tower cleanings once to twice per year are very, very important to do. All right, so we kind of talked about this earlier too, but bacteria produce kind of like a slick, slimy feel. They're highly insulating. Bacteria itself is not visible, but once you do start forming those bioslimes, it will be visible. And again, it just creates a lot of problems: corrosion, biofouling, insulation, bad heat transfer, and obviously, in some cases, Legionella. And Legionella does tend to proliferate when other bacteria are in higher numbers as well. It likes to kind of live underneath existing biofilms, and that's why sometimes Legionella tests can be performed and you won't have a positive result, and literally a day later you can run a Legionella test and you might have a positive because you might have a pump that cavitated, or just the vibration from a cooling tower fan loosens a biofilm that might be present or something like that, and just by that biofilm loosening up a little bit, Legionella that was living within that biofilm ends up being released into the bulk water, and that can cause problems. So. And that is also one of the reasons that Legionella is so difficult to treat. You know, a lot of people are like, oh, I got Legionella, I have terrible water treatment. Not necessarily. It's not having Legionella should be the result of good water treatment, but you can have really good water treatment and sometimes still end up having a positive hit with Legionella, just because of...
There's a lot of dead legs, correct?
Yeah, dead legs, there's a lot of problems. Like dead legs, huge problem. One of the big problems with dead legs or offline systems is that bacteria is just sitting there, it's stagnant, it can grow, and like I said, with a pump cavitating and shaking a pipe, that can cause biofilms to break up and Legionella to be released. You can also have, like with dead legs, you can get like a little bit of burping sometimes in a dead leg, where like the water is trying to make its way down there, but it can't. It will kind of like burp up some of the junk that's sitting in a drop leg or a dead leg. So those are things that, especially in healthcare facilities, it's really important to have not only a water management plan, but also have somebody come in and do kind of like a Legionella assessment. Like just look at the whole facility, top to bottom, all the piping, identify if you have dead legs, identify offline systems, offline piping with no flow for periods of time, things like that. I mean, there's so much that goes into it. It's really a difficult thing to deal with, and water treatment people get blamed for it almost exclusively, but a lot of times there is more to it than just the chemical treatment. All right, so keys to effective microbial control, system design and operation, we were just talking about that. I mean, minimizing dead legs, minimizing offline systems, minimizing low flow, no flow situations. Obviously, biocide additions through water treatment is very, very important. Monitoring biological growth with dip slides and things like that, or lab testing can be really important as well. And then also cleanings and disinfections. So doing your proper preventative maintenance on your systems is huge. We're not going to talk about closed systems too much today. But I mean, obviously, most of you probably have closed loops in different places. Hopefully you don't have water loss, at least too much water loss. But one of the problems, especially in closed systems with leaks, when you do have water loss, is you're constantly bringing in makeup water. That can introduce bacteria into the system. That can cause corrosion problems. And obviously those leaks are also diminishing the amount of available inhibitor that's in the system to help prevent corrosion as well. So checking those closed loops at least quarterly is important. Make sure that your nitrite levels, if that's what your water treatment provider is using for inhibitor, make sure that's in range. And then if you do have leaks, testing for microbial activity is important as well. Alrighty. Kind of talked about this earlier, compressor being the primary consumer of electricity on a chiller. All right, so we got into this earlier as well, but deposits, bioslime, scale, condenser, tube surfaces are not able to cool the refrigerant as efficiently. It's going to make your compressor work harder. And so like Chem had brought up earlier, that can cause high head pressure, can cause the system to shut down. But I mean, more than that is just if your approach temperatures are getting high, it's an indication that you don't have good heat transfer and your energy costs are just going to be very, very high compared to if you had good heat transfer. So this is just good to know. Each 1 degree refrigerant temperature by design increases energy requirements by 1.5%. So, I mean, that kind of illustrates how your costs exponentially go up just by 1 degree of increased approach temperatures. And then we talked about this earlier too, down on the bottom, slime is 4 times as insulating as mineral scale. So just always be aware of that when you're doing your annual inspections. A lot of times people are opening up chillers just looking for scale. If you're feeling something a little slick and slimy in there, even if it looks clean, that very well could be a bioslime that is causing heat transfer problems that you might not be aware of. All right, so in addition to that, just to kind of continue to illustrate it, a 1,000-ton cooling system operating at 50% load, a biofilm of just 0.01 inch in thickness. Under those system operating conditions, can increase your electricity cost over $51,000 a year. So it's really, really important to make sure that bacteria levels are kept low. And you're gonna see that on your approach temperatures. So it's not just during your annual inspections. You're gonna see evidence of that. Like you're gonna have, if your approach temperature is supposed to be 1 degree or 1.5 degrees or something like that, if you have a biofilm that's costing you that much money, it's gonna reflect itself in your approach temperatures. So if y'all are checking that and logging that, you should see it. Okay, so we kind of talked about this earlier, but the heart and soul of water treatment is controlling cycles, controlling conductivity set points, and then obviously making sure that you're feeding the right amount of inhibitor, feeding the right amount of biocide. I'm a really big believer in customers taking ownership of their water treatment. I know a lot of customers feel like, hey, you're doing my water treatment, this is your baby, but if your water treater's coming once a month or twice a month, that's great. But there's a lot of other days that tests aren't being run. And so I encourage everybody, when you are dealing with a water treatment company, ask to be trained, ask to be involved, ask to take accountability over your water treatment. Your water treatment person is going to be a better partner to you, and that communication is key. I mean, Shannon, he runs a lot of tests. Before him, Ronnie was running a lot of tests. You check daily, I think, right? Yeah, and whenever there's a problem or something that he's confused about, he can call me and we can work through it. But you're going to have better results if you're doing testing in addition to your vendor coming and doing testing as well. And also, nowadays, we also have online monitoring that's available. I mean, we have it, other companies have it. that's one way that if you just really don't want to do testing or have your operators do testing, you can also purchase online monitored equipment where you have 24/7 real-time data showing you all of the parameters and everything. So we kind of got in-depth here on cycles and how all that is calculated, but the really simple version of it is whatever your tower conductivity is divided by your makeup conductivity, that's how many cycles you're running. This is just to illustrate what's actually happening, right? But that's how the calculation is done. And it's linear with the amount of dissolved solids as well. So like if your tower conductivity is 1,000 and your makeup conductivity is 200, that's 5 cycles. If your makeup hardness is 50, at 5 cycles, your tower hardness would be 250. If you're feeding the right amount of inhibitor. If there's not enough inhibitor, you're going to see your hardness lower than what you would anticipate in the tower. So if you are anticipating it being at 250 at 5 cycles and it's at 200, that means some of that mineral content is going somewhere, and it's probably coming out on a heat transfer surface. So these are some different inhibitor feed methods. Probably the best is proportional to metered makeup, which is how we do it here. And so basically for however many gallons of makeup, we've calculated how much inhibitor should be going into the tower. That's a great way to do it. Fluorescent trace probes are a newer way to do it. We do that on online monitored systems. That's a great way as long as you're making sure that the probe stays calibrated. But the fluorescent trace is generally called PTSA. Unless it's Nalco, they call it TraceR. But basically, the inhibitor has a fluorescent trace that's blended in ratio with the actives in the product, and that's a great way to control inhibitor feed as well. Proportional to bleed time is probably my third favorite way to feed it, but it's good as well. Basically, that's just you're feeding your inhibitor as a percentage of bleed. So if you blow down for 20 minutes, your inhibitor is going to feed a percentage of that amount to replenish the losses to blow down. Percent timer is my least favorite way to feed. It's just not accurate because it doesn't take into account load conditions. Your blowdown is where you're losing your chemical, right? And so you want to either feed in proportion to blowdown or in proportion to makeup. If you're just feeding on a timer, you could have low heat loads and less blowdown and you're going to overfeed chemical, or you could have high heat loads and more blowdown and underfeed chemical. So it's just not the right way to do it. All right, so biocide feed methods. Generally, we feed biocide on timers. It's a slug dose. Typically, you're going to feed an oxidizing biocide Monday, Wednesday, Friday. Your non-oxidizing biocide is going to feed Tuesdays and Thursdays, or sometimes just Tuesdays. But that's generally how that's going to be set up. Biocide feed is based on system volume. And it needs to also be adjusted based on other variables like how dirty is the cooling tower? When was the last time it was clean? Do you have biological issues? Do you have dead legs that are burping? So there's other things that kind of come into all that, but generally one of the best ways to make sure that you're feeding the right amount of biocide is to test free chlorine an hour after the feed. If you've got 1 ppm of available chlorine 1 hour after your biocide feed, you're feeding enough biocide. So this is a controller. I'm sure a lot of y'all have seen something that looks like that, but that's what's going to control your blowdown by monitoring conductivity. You're going to control your inhibitor feed with that. You're going to control your biocide feed with that. That's kind of the heart and soul of the chemical feed station. There's just kind of another example. Obviously, y'all probably know what pot feeders are for closed loops, so we're not going to get too much into that. And that's kind of the end of the cooling section. We don't have a ton of time to get into a whole lot of boiler stuff, but if anybody has any boiler questions, I'd be happy to address any boiler questions. Anybody? Nothing? No? Okay. No. I mean, boilers is kind of the same concept, really. I mean, you know, in a cooling tower, you're evaporating water, right? And you're concentrating minerals because you're evaporating water. In a boiler system, you're making steam, if it's a steam boiler, and because of that water loss to steam, you're concentrating minerals. The main difference between the two is there's an inverse relationship between temperature and solubility of minerals. So in a boiler, you have high pressure, high temperature, so you can't have as much dissolved mineral content as you can in a cooling tower. So that's why soft water is so important for steam boilers. Just a little bit of hardness is going to precipitate and cause scale in a boiler just because of the temperature, whereas in a cooling tower, you don't have 300 degree water, you have 90, 95 degree water or something like that. So you're not going to have the scaling problems that you have in the boiler. But for boilers, conductivity control is really important. Good quality feed water is important. So your feed water is made up of soft water from your water softener and condensate return. The more condensate you have, the better, because that's the less soft water you have coming from your water softener, so it's less strain on your softener. Condensate is pure water, basically. So the more condensate you can capture and return to your feed water, the better off you are. And then you have to supplement that with a good working water softener, because if you have any hardness in a boiler system, at least a steam boiler system, it's going to be very, very difficult for the chemicals to do their job. Anyway, that's kind of what I wanted to talk about today. And anybody have any questions? No? Anybody learn anything?
On the boilers, how often do you told me that you should
Pop the pop off. What do you mean?
got like a relief valve on the boilers?
Okay.
You should bleed it every day.
What kind of boiler? You talking about hot water boilers, steam boilers?
Water tube boiler.
But closed loop or
Yeah.
steam? Yeah, I don't know. I mean, it would probably just depend on the system design. If it's closed, you shouldn't be using water. That sounds like that might be more of a that sounds like that might be more of a
The relief valve.
yeah. It sounds like that might be more of a pressure issue. Yeah. Yeah. Thank y'all for coming. Really appreciate it. And, yeah, for sure.